Welcome to qnawire.
Hi. So for this question, the first thing that we are going to do is to draw our different d orbitals that we can have in the metal. So I'm going to try to draw them as fast as possible. Something like this. This would be dxy. Next up, we're going to have in the y set. This is going to be dy set. Remember that these guys are in between. Next up, we can get x set, set and x. Like this is the general shape. Dy set, dx set, and the other two that I have left are we have dx squared minus y squared, so y and x. Whoops, x and y. Perfect. This is going to look like this on the x and y axis. So this is dx squared minus dy squared. And finally, the z squared that looks, this is the z axis. We really do not care too much about what else is happening here, because here we have like a small donut, right? Okay, so now with these orbitals, we can go ahead and write down our compound, which is going to be in trigonal bipyramidal configuration. So we're going to have two ligands over here. We're going to have a ligand over here and two ligands on this axis. So what we are going to do is let's call this the z axis. Then what we are going to do is say that we have one of the ligands going in the x-axis, and then the y-axis is going to be a little bit off over here, right? So remember, in crystal field theory, what we are assuming is that every ligand is acting as a point charge, and the stability of the orbitals depend on the repulsion interaction that we are going to have. So the larger the interaction is, the higher in energy the orbital is going to be. First of all, let's look at the dz squared orbital that we have over here. Well, what we can say is that it is going to interact with two different ligands. The interaction is quite direct. They overlap almost perfectly. So that is the one that is going to be higher in energy. So in our diagram, let's draw the middle point. This is going to be increasing order of energy. And the one that is going to be higher is the dz squared orbital. Next up, what we are going to see is what other orbitals are going to have similar interactions. So, first of all, let's look at the x squared y squared orbital. Well, in x squared y squared, we have the orbital directly on the x and on the y axis. And over here, as you can see, the orbital would be interacting directly with one of the ligand, and it's right in between two of the other that are in the plane. So that is another one that is going to be a high interaction. What else do I have in that axis? Well, I also have the xy component, right? In the xy component, the orbital is right in between. And guess what? Let's draw that interaction in green. Whoop. This would look something like this. Uh, Something like that. So this would be the dxy orbital. And I'm going to draw in purple the x squared y squared one. So this would look something like this and like this. As you can see, for both of them, we have a direct interaction with one of the orbitals and with one of the ligands, and the rest of them are going to be right in between the region of the d orbital. So that means that both of them are going to be degenerate in energy. both of them are going to be stabilized because we only have interaction with one of them, and the other interactions about repulsion. So we're going to have dx squared minus y squared and dxy. And now let's see what happens with the xz and yz axis. Well, they're going to be like in diagonal, like looking up, but none of them are going to have a direct interaction, a direct overlap in between the d orbital and the ligand. So they are going to be the lowest ones in energy. In this case, this becomes the xz and the yz. And this would be the sketch of the crystal field splitting for trigonal bipyramidal complex ion. And that would be all. Thank you very much.